get set up for, oh, here we go, current slide. Okay, before we get started on that, let me go over a couple things. Finally, Thursday afternoon, I had some free office hours, fairly much uninterrupted. So I did get, I think I had a few things to correct on your syllabus. I already had gotten the research paper topic corrected and my locator card corrected for them. I'll talk about that in a minute. So all this is under Blackboard, under content. The syllabus, research paper instructions, locator card, and I can't recall if I found any YouTube videos that students had turned in or that I had found for this course. You might check and see. But I think after that is your PowerPoints. So I've got the PowerPoints for each of the chapters we're going to be covering. So those are on there, and then I put the link so you can get to the previous classes we've had. So I think it's all out there now, but one problem. Sometime Thursday or so after I had done all this stuff, I found out that it sounded like they are going to pay me for an overload. But if they pay me for an overload, that means I have to extend my office hours. So I'll have to go in and change on your syllabus and on my locator card what the new office hours are. Basically, nothing new on Monday, Wednesday. I don't have any more time on Monday, Wednesday. But Tuesday, Thursday, I'll be here after 3:30, probably until it's going to average around 5:30. Some days I might have to leave as early as 5:15 because sometimes I have to be at Homewood before 6. And with traffic at that time of day, I have to leave a little early. Other days, I won't have to be, so I'll stay later, like 5:45 or 6 o'clock. So on average, about 5:30. I'll have to figure that out and put it out there. Okay. I think that's most of what I had to talk about. I can't think if there's anything else. If I do, I'll hit it as we go on. All right. I guess I do want your input on this. What we're going to do today, we're going to start in Chapter 2 and get as far as we can in Chapter 2 between now and 3:30. Okay? At 3:30, we're going to start the lab for Chapter 1. Okay? Now, the question is, when do you want your tests? They're take-home tests, remember. Y'all asked for them. You got them, Toyota. So if you want the test now, I can give them to you. Or if you want to wait until right before you do the lab, you can get them. Or right after you finish the lab, when you turn in the lab, you can pick up your test, whatever. Does anyone particularly want it now? Okay. Well, just remind me, don't leave home without them. I mean, in other words, don't leave here without picking up your test. Okay, Chapter 2 is talking about motion in one dimension. Okay, Chapter 3 will be talking about motion in 2 dimensions, and that's where we'll bring in vectors that we talked about last time. This is one place the slides are not matching the book as well. Well, when we're talking about motion, we're talking about a concept called dynamics. In other words, things are moving. Statics, and many of you, or any of you pre-engineering, I'm guessing not, but if you were, you're going to have a course in statics and one in dynamics, or you'll put them back together. But in other words, dynamics is the branch of physics involving the motion of an object and the relationship between that motion and other physics concepts. Okay, so in this chapter, we're only going to deal with the motion part of it. Then in subsequent chapters, we'll deal with the relationship with the other physics concepts. Kinematics is part of dynamics, and in kinematics, you're interested in the description of the motion, and then you're not concerned with the cause of the motion. And again, that's something we're going to hit in a later Chapter 2, basically forces. So kinematics is basically what this chapter is going to focus on, kinematics in one dimension. And I was psychotic or psychic 1, and I put you down already. It's here, so gotcha. Okay. I got your names crossed up is what I did. Okay. Oh, did y'all get that? Okay. Some of these wordy type slides I moved through too fast, realizing you're probably By the way, since all the slides are out there, if you wanted to print them off ahead of time, save yourself some writing. But on the other hand, writing is more of an active learning thing than reading, so you may still want to find that this is more sticks with you a little better. Did I move off the first slide too fast? I don't think so. Now, I know there's probably some pre-physical therapy majors in here, right? Let me guess, some of you majoring in maybe kinesiology? Yes? Okay. Kinematics is study of motion. Kinesiology is the science of motion, you might say. Specifically human motion or structural motion. So you'll see some connection between this. Everybody got it now? Some people still writing. Okay. Don't let me move too quickly. Okay. Again, the wordy type slides I tend to go through, read them too fast, and move on. And again, the other physics concepts will come up in subsequent chapters, and causes for motion will come up in subsequent chapters. But these next two chapters, this one and the next one, are basically kinematics, dynamics, study of motion. This chapter in one dimension, next chapter in two dimensions. This chapter we're only going to deal with plus or minus to describe motion. Next chapter we'll deal with vectors to describe motion. All right, everybody got it? Okay. So what are the quantities we deal with in motion? Any motion involves three major concepts. Move from here to there. That's the displacement. You describe that typically with a distance, but the sort of the physics term is displacement, and specifically the vector term. Though we're not going to talk about vectors that much in this chapter, that is your vector term. That's both a distance and a direction. Velocity is the time rate of change of your displacement. In other words, your displacement divided by time will give you a velocity. Now, the scalar quantity is speed, the vector quantity is velocity. Well, once you got that down, guess what we do? Take the time rate of change of velocity, and that gives you acceleration. Okay? So in physics, you're going to hit this over and over and over, especially in this course. We'll study a feature of motion energy of various things. Next thing we do is take a time rate of change of it. In other words, take that thing divided by time, this thing divided by time. See, displacement divided by time is velocity, velocity divided by time is acceleration. Okay. These concepts can be used to study objects in motion, and that's what we'll be doing. Okay? Now, I would say there's one more concept they just sort of took for granted here, and I said it 2 or 3 times. Time. The ratio of displacement to time is velocity. The ratio of velocity to time is acceleration. So that's sort of a hidden thing here is time. Okay? So it's not hidden. We'll actually be using it. Can I get your name, please? Second? Tiara. Okay, got it. Okay, is it still raining out there? Yeah, I saw it. Boy, it was pouring earlier. Okay, has anyone else come in since I called roll? Okay. All right. Anyone still need this? Okay. And again, these are all out there. So let's look at a brief history of motion. Actually, the study of motion. Motion's been around prehistorically, okay? But when you see the word Sumeria, that's different from Sumeria, but Sumeria, what comes to mind? Maybe nothing. Think Babylonia. The ancient Sumerians lived in the typical area where Babylonians lived later. You heard them talk of the Fertile Crescent, the Tigris, Euphrates Valley. The early civilizations there were the Sumerians, and then along the Nile River were the Egyptians. Okay, and these two civilizations basically were forming about the same time. Now, when they were dealing with motion, they were dealing mainly with the motion of the heavenly bodies. These were the early astronomers, okay? And they dealt with that. Later, the Greeks came along. This was a fair amount later, too. It was still BC. Also, they began to use motion to understand. They also sought to understand the motion of heavenly bodies in systematic and detailed studies, and they were all looking at the geocentric model. In other words, the Earth being the center and everything else moving around it, because in the night sky and the day sky, it looked to be that the other objects moved and we were fixed. Of course, we know now that's because we were spinning. They didn't realize we were spinning. They didn't feel like they were spinning, but indeed, that's what made the stars and the sun appear to move, whereas in reality it was us moving. But this also is dealing with mostly heavenly bodies. But the Greeks went a little bit further. One of the Greeks that did this was good old Aristotle. Now, we'll talk about him probably a little bit later too. But he began looking at motion on Earth as well as motion in the heavenly bodies, and he said there are two completely different kinds of motion. He said that was the celestial motion, and on Earth you had terrestrial motion. Okay, and they followed different rules, different laws, and everything. Of course, later Galileo came along and said, nope, they're all the same, and Isaac Newton, even stronger, said, nope, they're the same. Okay, but that was the geocentric model. Modern ideas of motion, especially heavenly bodies, came along, and this is not all that modern, but Copernicus. I think he was Polish, if I'm not mistaken. He developed the heliocentric model. Galileo heard about this, he started studying it, and he reinforced this. He made astronomical observations with a telescope. Now, Galileo did not invent the first telescope. Can't remember the name of, I think it was Dutch or somewhere in Northern Europe guy who came up with the first telescope. Galileo read about that too and started fiddling with it and greatly improved that earlier guy's telescope. Big time. And he was able to see much further, much clearer, much more magnification than the other guy did. So he started making observations with the telescope that reinforced Copernicus is pretty much an empirical heliocentric model. He started collecting experimental evidence for the description of motion. Not just celestial motion, but motion, what Aristotle would have said, terrestrial motion as well. And in his quantitative study, he said, these are not two different kinds of motion. They are indeed the same. But he didn't quite reach that conclusion, but good old Isaac Newton did. But he started collecting the experimental evidence that better described motion than anyone had before, especially of the things. In fact, one of the things that gave it away to him, he was supporting the heliocentric model, but on his telescope, with his telescope, and he had to be very careful with it, he saw that indeed the sun did spin. Okay? Because of sunspots and things. Again, he had to be very careful. He couldn't look directly at the sun, especially through a telescope that focused. He would have burned out his retina and he'd been blind. But he did and saw that the sun spun. But not only that, with his telescope, he saw Jupiter, and he could tell that Jupiter was spinning. He saw the 4 biggest moons of Jupiter, and he could tell at least that 1 or 2 of those were spinning. And all of a sudden it said, wait, if all these bodies out there are spinning, why wouldn't Earth be spinning? That could account for the relative motion of the stars across the sky, and therefore the heliocentric model of Copernicus has more foundational evidence and belief for that. So this is where our modern ideas of motion started coming from. So let's look at these. This is moving to section 20 or 2.1. These three aspects of motion. The first was displacement. That is a measure of an object's position. Okay? Now, an object's position, you really need to know what you're talking about or where you're measuring from. The distance from me to that table is different from the distance from you to the table, okay, for most cases, okay? It would be different from the people down in room 263 to that table, okay? So position is defined in terms of a frame of reference. Where are you dealing from? Are you measuring, and then how you measure too. People down on the first floor, the table might be above them, at a certain distance. Here is at basically the same level. So basically you make a choice of your coordinate axes. Now, most of the time we use what we call rectangular coordinate axes, but not always. And that is often called the Cartesian system because René Descartes came up with that, and he was the first to tie analytic geometry with algebra by using Cartesian coordinate system, the rectangular coordinate system. So this defines the starting point for measuring the motion or any other quantity. And in one-dimensional motion, generally we count that on the horizontal axis or on the vertical axis. Now, the book, and I'll use it to X and Y, but basically being a little more precise, I think it's horizontal and vertical. Because we're going to talk about one-dimensional motion either as horizontal motion or vertical motion. Now, actually, in the lab we do for this chapter, which will probably be next time or probably next time, actually our axis will be slanted because that's what we're going to be measuring, inclined plane, but it'll still be one-dimensional motion. Okay. Oh, did everybody get that? Okay. So that's position measured in terms of a frame of reference from some origin, from some fixed point along some fixed coordinate system. Okay, so what is displacement? Is defined as a change of position. Okay, if I'm standing here, I move to there, then I have displaced myself. Or if I throw my book over there, or roll a pencil over there, or something else, I've changed the position. I had a position, I had a new position, the change of position, and this delta basically means difference. It's the Greek symbol delta, capital delta, and that means difference in x. And the difference in anything, it doesn't have to be x, this is horizontal motion generally, that would be x final minus x initial. If I started here and moved to there, that would be x final, this would be x initial. Position final minus position initial, that would be my change of position, delta x. Okay? Always final minus initial. The F stands for final, I stands for initial. You haven't picked up on that yet. The units, if you're in the SI system, and most of the time this book will be there, that will be in terms of meters. If we're talking about an ant crawling across the desk, meters would be a bit big, so we might use centimeters. In the lab, not this time, but next time, we will be using centimeters as our basic unit because we're only going to be measuring short distances. But in general, SI, we would use meters as a displacement unit. All right, so here are a few displacement examples. If this is position A, that's position B. Okay? Well, let's use the cards here. If your initial position is on meter marker 30, okay, not mile marker 30, meter marker 30. That's where your car initially is. Your final initial position is over here at meter marker 52. What's your change of displacement? Your change of position? It would be 52 final minus initial 22 meters. You travel 22 meters to get from here to there. Obviously, I mean, you can see that. One-dimensional motion. The displacement is positive, indicating the motion was in the positive horizontal direction, x direction. You're moving ahead. But what if you started here at position C? That's at 40. No, 38 they say here. I don't know how to get that. 38. And your final position was way over here at F. And that's minus 53. Which way have you moved? Always F minus I, x of F minus x of I, 53, negative 53 minus 38 would be minus 91. You moved 91 meters in the negative direction. According to this, you were backing up 91 meters. It's almost a football field length, by the way. The displacement is negative, indicating the motion was in the negative horizontal direction, or in other words, that you were moving to the, basically, we would think left of where you started. Okay? Now, this would be C, D, E, F. That would be progression in that direction. Negative of the, see, notice what you've done here, what this is always assuming. You find some zero position, that's your coordinate system. You've defined to the right being positive, to the left being negative, so any motion you have here, if you're going to the right, it's positive. If you're going to the left, it's negative, because you defined that to begin with. And that's usually the definition we'll go by. There will be times we'll do things a little backward, but that'll be for a reason. Okay, now let's do the graph of this now. Let's say we started at 30, so that was at time t equals 0. Now we've got a graph of displacement. Now, even though that's horizontal displacement, we put it on the vertical axis. Why? Because the independent variable is time. Displacement is a function of time rather than time being a function of displacement. So we'll put always the dependent variable vertically, horizontal variable horizontally. Wait, I said that. Independent variable horizontally, because the vertical depends on the horizontal. That's the standard. So this is going to be time, even though this might be horizontal motion, we're going to put it in the vertical axis, because your independent variable goes on the horizontal axis. So, at time t equals 0, you're starting at position 30. Okay? Then at position B, 10 seconds later, because you see your time is measured in seconds, your displacement is measured in meters, we're in the SI system. 10 seconds later, you're at position, what they call it, 52 or 53, something like that. So here you are there. Now, we'll get to this later. This would indicate your average displacement. This is your actual displacement. Okay? You started off a little faster, you ended up slower, but your average was right there. We'll get there later. Then you move to position C, somewhere around 38, I believe it was. Okay? Then you move to D, which is at 0. Then you move to E, which looked to be about minus 37 or something like that. And then you finally ended up at position F, which is minus 53, 54, whatever that was. Okay? And that's where you ended up here. And this gives the time interval, and this gives every 10 seconds. So that's why those positions were chosen, even though their displacements were variety, they were every 10 seconds. Okay? Now, we're going to do more with this later. But while we got it up here, your change of displacement per change of time, guess what that gives you? Change of displacement per change of time time rate of change of displacement is velocity or speed. Okay? And this is an average velocity, indicating you're probably going faster here, slower there. That you're almost at a stop here. So this is your average velocity, the slope of that line, delta x over delta t. That's the slope. x2 minus x1 over t2 minus t1. That's your slope of that line. They call that a secant line, by the way. 2 points on the line. The average speed between that is the slope of the secant line between those, even though the actual motion was following the curve, not the straight line. That gave you the average. When I drove here this morning, when I left the house, I backed out of the driveway, going in the negative direction, okay? Then I turned and went slowly to the first turn, make a right, went for a few blocks, made a left, and every time I had to stop, slow down, change direction. I was not going at constant speed any of that time. Now, once I finally got on the expressway, I was going fairly close to a constant speed for much of the time, but, when the rains came or when trucks got in the way, I had to slow down, or when I was trying to pass on one, I might have sped up a little bit. So, very seldom do you go at a constant speed, which would be what the straight line indicates. Most of the time you're going at a curved rate of displacement, okay? Now, there is a picture on page 32 that's not on your slide set, for those who have the same book, same edition. It's a picture of a canyon on the surface of Mars. It's called the Vallis or something like that, Maniris or something like that on Mars. And just looking at that picture, you don't know how big that canyon is. Now, lots of interest to that there could be a canyon on Mars. Typically, what forms a canyon?
Water.
Say again?
Water.
Water, exactly. Water eroding the soil. The Grand Canyon was made by water eroding the soil away. Just by any canyon here on the surface of the Earth, generally always is caused by water. If they found a pretty good-sized canyon on Mars, what would that indicate? At some time in its past, it may have had a fair amount of water. Now, that's interesting. Very interesting. What would be some reason water on Mars would be of interest? Say again? Did you say supporting life? Is that what you said, or something else? Okay, yeah. That's how you wonder, was there ever life on Mars? There's no evidence of surface water on Mars any longer. Now, just below the surface, you have a fair amount of ice near the polar areas, and I think they've detected water subterranean, but on the surface, hardly any water anymore, if any, unless it's in the form of ice near the poles, like we have or have had. So it might be of interest to know, well, how big is this canyon? I don't have a reference here. Well, the B part of the picture shows a scale drawing, and they put the U.S. over this canyon. It's almost the length of the U.S., the contiguous 48 states. It goes from, it looks like approximately Virginia to Nevada or so. That's most of the country. And for them to have a canyon that big, they must have had a fair quantity of water as well. So, interesting picture. No proof of it, it's just by our conjecture. That's what could have caused that canyon. Okay. Now, We already talked in the previous chapter what were vectors and what were scalars. Someone give me a brief rundown of what the difference in a vector and a scalar.
Vector has a direction.
Has a direction, whereas a scalar doesn't. Both vectors and scalars have a magnitude, how much of it you're talking about. A vector has a direction with that, a scalar does not. Like my mass, it's just that. You know, I don't have a direction associated with my mass. Force it does, pounds does, mass doesn't. Okay? Time doesn't have a direction. Those are scalar quantities. But velocities, displacements, accelerations, and later we'll talk about other things, do have direction, and they would be vector quantities. Whereas distance, speed, those are just scalar quantities. They're just numbers indicating how far or how fast without any direction associated with them. So vector quantities need both magnitude, size, and direction to completely describe a vector, generally denoted by boldface type and with an arrow over the letter. Since this chapter is dealing with only one-dimensional motion, we can indicate our motion by plus if it's going that way, minus if it's going this way. Plus if it's going up, minus if it's going down. Since we're only dealing with one-dimensional motion, a plus or minus is going to be our directional part of the vector quantity. Okay? Scalar quantities are completely described by magnitude only, and typically they're always positive. Okay? Typically they're positive. For instance, I can't have a mass of negative 15 grams. Okay? That means I wouldn't be here and I'd be less than be here. Okay? Yeah, you just wouldn't. But minus 15 miles per hour or feet per second or meters per second would be indicating going in a direction in the negative of where I started from. Okay? So scalar quantities typically are completely described by magnitude only, and generally that magnitude is considered to be a positive quantity. Okay? There's no reason to indicate negative if it's a scalar, okay, because you only have magnitude. Did everybody get that? I turned maybe too fast. Is that okay? Okay. Wait a minute. Let me know if I'm mistaken. Boy, it's raining again. Nice. Wet. Okay. Hope, and I'm pretty sure I left my windows up. Otherwise, it's going to be a wet drive home. All right. Everybody got it? Okay. Now, displacement isn't distance. Distance isn't displacement. Displacement of an object is not the same as the distance it travels. Displacement, okay. Displacement, if I started here and wound up there, that's the displacement. The distance, if I started here, meandered about here, and maybe went over here, and possibly backed up a little bit, went in a circle, and then came back, and finally came here, the distance I would be traveling is a lot further than the displacement. I started there, ended here. That's what displacement is. Distance is actually how far I moved to get there. Okay? I can remember my younger brother talking about his boy. He had two girls and then finally had a boy. And Daniel was pretty athletic and stuff, but he couldn't get, his dad was too busy, his sisters didn't want to, couldn't get anyone to throw the football with him. So he would throw the football up in the air and then run and catch it, before it came down. He spent a lot of time doing that. If he had thrown the ball straight up in the air, he wouldn't have to run anywhere. Okay? Catch and caught it at the same point, that would be, the ball traveled quite a distance, depending on how hard he threw it, before it came back down, but guess what? Its displacement was zero, because he caught it at the same place he threw it. So the displacement would have been zero, whereas the distance the ball traveled would be twice the height. It went up a certain height and came down that. So its distance is twice that, displacement absolutely zero. Okay? And when he was wanting to move some, he'd throw it that way and run under it and catch it. But it would go a lot further than he would. Okay? So displacement is not the same as distance. They are measured in the same units. If I go from here to there, I could measure that in meters, feet, inches, yards, furlongs, whatever. But for both the displacement and the distance, but they wouldn't be the same quantity. Just because they have the same units doesn't mean they're measuring the same thing. Okay? Okay, moving on to speed. Now, in everyday English, we usually use the term speed and velocity as if they were interchangeable, synonymous, okay, meaning the same thing. In physics, they don't quite mean the same thing, just like distance and displacement don't mean the same thing, because average speed of an object is defined as the total distance traveled divided by the total time elapsed. And generally, distance traveled is a positive thing, time elapsed is a positive thing, so average speed is typically a positive quantity. And its formula, average speed is path length divided by elapsed time. Now, a lot of time for path length, math books will use S, and you could use that here. This one uses V. Velocity is distance divided by time. Okay? Speed is a scalar quantity. Average speed, instantaneous speed, they're scalar quantities. That doesn't mean they don't have units. Of course they have units, they just don't have what? Scalar. Direction. It does not have a direction associated with it. So speed is a scalar quantity, it's just a magnitude. Usually indicated with positive. So you could talk about a negative speed if you're backing up. Okay? You know that indicates a negative speed. Okay? But generally, distance is positive and time is positive, so speed will be positive. Now later you'll see we'll use V for velocity as well. So don't get this crossed up. I don't know if you can tell looking at it, but this is in italics. Okay? It's got a little slant to it. That means it's speed, not, and so is this and that. Those are scalar quantities. All of these are. So that's, and that's why they don't use S for speed, because sometimes you use S for arc length. So don't get those confused. This one uses V, not velocity, but speed, because it's italicized. It's a scalar quantity. Okay. Now, what in the world is average speed? It totally ignores any variations in the object's actual motion during the trip. Okay? When I left home this morning, like I said, I backed out of the driveway. Okay? Speed didn't care less. How far did I go? From the top of the driveway to the bottom of the driveway, measure that in meters, and that's how far I went. Not a negative quantity, even though I was backing up. Okay? Then I turned as I went back and went basically to the west on the street that I live on until I got to the top of the hill, take a right. It doesn't care what directions, what I'm actually doing. Average speed is just how far I traveled divided by how long it took. The path length and the total time are all that's important. Path length, how far did my wheels turn on the road, okay? Both will be positive, so speed is typically given as a positive quantity. The SI units are meters per second, okay? Everyday units, if I'm in my car, I don't want to measure that meters per second. I could, but I usually measure it in what? Speed in the car. On your speedometer, speedometer, the thing that measures speed. What's usually given it? Miles per hour. Distance over time. That's what you're measuring. So speed would be distance over time. The SI units, meters over seconds. Everyday English, miles per hour. Everyday, say if you lived in a country that used metric systems strictly or SI strictly, traveling in a car, you use like kilometers per hour, okay? Because that's what you talk about in trips. You don't talk about how many seconds it took you to get from home to Bessemer. You know, I didn't measure the seconds. I measured fractions of an hour, okay? The SI units are meters per second. Length per time. Everybody got it? Okay. Now, let's look at path length versus distance. We sort of already talked about this a little bit. Okay, but this is they're sort of mixing the words a little bit here. Distance depends only on the endpoints. Okay, again, this is for displacement purposes. Sometimes we talk about path length as being a distance, and it is. I wish they say path length versus displacement. That would be more precise here. Okay? The change of your position is SI was initial, F is final. Then this would be the square root of the change in X and the change in Y. Now, why in the world are they introducing this in the chapter in motion one dimension? I'm not sure. Because obviously here you're going in an X dimension and also in a Y dimension. But that doesn't make it any less true. But this is your path length versus distance. But like I said, I can't describe this motion as one dimensional because I'm moving around in a variety of things. But your distance is one dimensional. Change of S. Okay? You don't care how much you're weaving and whatever. This will take care of it. Now, I don't know. Does this formula look sort of close to anything you've seen before? You probably hit this formula before. What's it based on? If I were to draw this here, you give me two coordinates, an X and a Y coordinate. Pick out any value for X. Name a number for X. It could be positive or negative. Keep the whole numbers up. 5. Okay, and you said 5, so I assume plus 5. Okay, give me a Y. 7. Okay. You want that initial or final? Final. Okay, that's going to be your final. Okay? So, X of F is equal to 5. Y sub F is equal to 7. Okay. So I'm going to give me an X for initial. 2. Okay. A Y initial. 3. Right there. So there's your initial position. Okay. So X of I is 2. Y sub I is 3. Okay. What would be the distance traveled there? Call that delta S. What would that be? Not that hard, is it? XF minus XI. 5 minus 2. 3 squared plus 4 squared. 3 squared is plus 16. Pick the nice one, didn't you? 25. You did it have to come out that way, someone's either very lucky or very, very good. I'll say it's good, but I don't think. No, never mind, I didn't say that, did I? Okay, now, is that 5? What if this had been final and that initial? What would have been my distance in? This would have been final and that would have been initial. What would have been the distance in? 5. The distance, the direction doesn't matter. This is a scalar quantity. The distance does not depend on what happens between the endpoints. If I had gone like this, here's initial, and I went like this. How far did I travel? A lot further than 5. What was my displacement though? The actual was just 5. This does not depend on what happens between the endpoints. It's the magnitude of the displacement, not how far you actually stepped in that process. The path length will depend on the actual route taken. Okay? Now, again, they usually use S to be path length. Now, I find it sort of obnoxious that they're using these symbols differently from what is kind of the convention. The important thing is you understand the concept. Okay. Now, unfortunately, all that's doing over there doesn't get recorded on the on Screencast-O-Matic, so that some of that may not make sense for people listening, but I just didn't have a lot of room to draw on this. Okay, velocity. Speed, distance traveled per unit time. Okay, velocity, it takes time for an object to undergo a displacement. So the average velocity is the rate at which the displacement occurs. Okay? So average velocity is delta x over delta t. Now, here they change back to x, one-dimensional motion. Why they interjected that slide in there that had two-dimensional motion, I'm not sure. So this would be x final minus x initial. Now that one-dimensional motion could be like this. As long as you're only moving one dimension, that's still one-dimensional motion. And your change of time is always final minus initial. X final minus x initial over t final minus t initial. Velocity can be positive or negative, depend on, number one, the coordinate system you choose, and whether you're starting in the positive direction, negative direction, or where you ended up. Okay? If you're starting negative from where you ended up, and I started positive from where you ended up negative, then you went in a negative direction. So the delta t, by the way, is always positive. T final is always a larger number than t initial. The time since you started is always, the final time is always beyond the initial time. So that's always positive. So everything depends on the sign of your displacement. The average speed is not the same as the average velocity. Okay? Okay. Average speed is a scalar quantity only. Average velocity is a vector quantity. Direction is involved. Average speed, typically always positive. Average velocity could be positive, negative, or zero. Okay? It is raining. Big time. Remember, your time interval is always, always positive. Displacement may or may not be positive, negative, or zero, and that will determine your average velocity sign. But your time interval is always positive. Back to the Future, it was a movie, not reality. Okay, everybody got it? All right, continue with velocity. Direction will be the same as the direction of displacement. If your change of direction is from a small number to a larger number, that could be positive. If it's from a larger number to a smaller number, that would be negative. So if the displacement is plus or minus, then your velocity is going to be the same sign, plus or minus. That's sufficient for one-dimensional motion. Later, when we get two-dimensional, we'll use vectors to represent that. Right now, we'll just use plus or minus. The units of velocities are the same as your units for speed, meters per second, but that doesn't mean they're measuring the same thing. This is in the SI units, okay? Again, we could use kilometers per hour, we could use miles per hour, furlongs per fortnight. I mean, anything that's distance divided by time. Other units may be given in a problem, but generally will need to be converted to SI units, meters and seconds. Unless the whole problem is set up in miles and hours and stuff like that, then you don't need to convert. In other systems, U.S. customary, the standard unit is feet per second, but if you're talking about large distances over long times, that would be miles per hour. Okay? CGS is centimeters per second. C standing for centimeter, and S, of course, is always second. Okay? G would be gram here, whereas the SI would be kilogram. Okay. By the way, we're in 2.2 now. I didn't mention that earlier. By the way, I did skip over something. I wasn't turning pages fast enough. There is an example in the book, the tortoise and the hare. You may remember that from a fable, that you may have read about sometime, long time in the past. Pretty interesting little problem, pretty straightforward of how you do the calculations for that. So I'll let you take a look at that. And I did fail to mention something else, but I'll hold on to it just for a minute until you finish with this slide. I'll go back at least one slide here to talk about it. I'll give you a minute more. For those who did come in a little bit later, everything on Blackboard is out there now. The syllabus, the research paper instructions, locator card, PowerPoints, the link to previous classes on YouTube videos, they're all there. I'm going to go back a slide or two and point something else out. And the reason I do this, it's different from what's in the book. Okay? Only the intent, the way they're presenting is different. In the book, they don't put the word average, they put a bar here. That means average velocity. Okay? Again, I said speed was also a V, but it was italicized. But since this is not in the vector V, it's also italicized. This is average speed. Okay? So, again, I think the book's notation is a little sloppy. But in the book, this formula was given with a bar over the V, meaning average velocity. This shows V sub-average, that means average velocity. Just whether you write the sub-average or the bar, they mean the same thing. I forgot to mention that because I hadn't turned that page to show you. Okay. I think we covered that slide. So let's look at speed versus velocity. Okay? Here is a car. You got two cars, a red car and a blue car. Okay, the red car goes on the red path here, and he goes straight from P to Q. Okay? Here's your XI, here's your XL. Same for both cars, red car and blue car. The cars on both paths have the same average velocity, since they have the same displacement over the same time interval. Now, they didn't tell you that. They left at the same time. They got there at the same time. Okay? Red car went a shorter distance. Blue car went a greater distance, but over the same time interval, which had the greatest average speed. Blue car went like this, red car went like that, but it took them the same time. Okay, blue car went farther distance, but not further displacement. Velocity, exactly the same. Speed, not the same. The cars on both paths have the same average velocity, since they move the same displacement, initial minus final. That's displacement at the same time interval. The car in the blue path will have a greater average speed since the path length it traveled is larger. This is almost seems like it's contradicting what it said before, but it really isn't. They just said it fairly poorly before, as I pointed out. But this one went a larger distance in the same time. This one went a shorter distance, but it still took the same time. Blue car just went at a higher speed, but their velocities, initial minus final, same. Okay. I think they did a poor job with their displacement. They were calling distance what they should have been calling displacement. Okay. Now, how do we represent velocity? Velocity can be determined from a position-time graph. Average velocity equals the slope of the line joining the initial and final points of the graph. That's what I pointed out to you on the earlier slide. That was your slope of the, well, that was your secant line. That's your average velocity. Okay? And actually it was the slope of that was your average velocity. An object moving with a constant velocity will have a graph that is a straight line. Wherever that is, if it's constant velocity, it's a straight line. Okay. Wait, did you? A little bit longer. Okay. So remember what our graph is on this position time graph. Position is on the vertical axis, time is on the horizontal axis. Even though it may be a horizontal position, you put it on the vertical axis because it depends on the time. Time doesn't depend on position, but position depends on time. Okay, so that graph then, the average velocity is the slope of the line joining initial point to final point. Whatever that slope is, that's your average velocity. It's great to be in here taking physics rather than be outside getting wet. Okay. So all you do, if you have a plot, a graph, position versus time, find your initial point, your final point, calculate the displacement, change of displacement over the change of your time. That's the slope of that line. Okay. Now, if a car left at time 0 and was at negative 20 meter marker, okay, and then 10 seconds later was at the 0 meter marker, and 20 seconds after that, so a time of 30 seconds, up at 40 meter marker, and going along the slope of this line, which is rise over run, which is 40 minus a minus 20. Now when you subtract the negative number, you change signs and add. So that would be 40 plus 20 would be 60 divided by 30. That's going 2 meters per second. 2 meters per second would be the average speed, and if it traveled exactly that path, that's the average velocity. If it traveled exactly that path, it would also be its average speed. The slope of the line is the value of the average velocity. Slope of the line, the value of the average velocity. Now, like I said before, if this had been doing like this, so its actual displacement was further, average speed is the same, but displacement is further, then it had a higher average speed than its average velocity. Okay. But we're not doing that. We're only looking at average velocity here. Okay? So here's a few notes on slopes. The general equation for the slope of any line is change vertical divided by change horizontal. Back in math class, you called that y2 minus y1 vertical over x2 minus x1 horizontal. Okay? Just remember now in physics, the horizontal and vertical could stand for different units. Displacement vertical times horizontal, then it would be meters per second. So you would have different units there. The meaning of a specific slope will depend on the physical data being graphed. What are you graphing? What are you putting on the vertical scale? What are you putting on the horizontal scale? Depending on what you're putting there, if it has units, then your ratio will be in the units of the ratio of the units you have. Slope often carries units. dy, y2 minus y1 over x2 minus x1, if both of those are measured in inches or meters or furlongs or whatever, then they would have no unit. That would just be a slope of a line. But if the vertical axis has units, the horizontal axis has units, and they're not the same units, then slope also carries with it units. And most of the slopes we're going to deal with will be dimensional slopes. They will represent speeds or velocities or other such things. Okay? The next lab we do will actually be calculating some velocities, and typically we'll measure the distance in centimeters, the time in seconds. So this velocities will be in meters per second, average velocity in meters per second. Your typical average accelerations will be in meters per second, meters per second squared. Okay. So most slopes that we'll be dealing with will carry units along with them. They won't always be time units, but quite often they will. And when you see something like meters per second squared, you don't have to say, what in the world is a square second? There is no such thing, but it's meaning per second per second. That's what they mean by per second squared. We're not there yet. We'll get there in a minute. Average velocity, if it's not a constant velocity, the last one was, okay, this is not. This had a positive displacement here, went from 30 to 57, I think it was, or something like that, 52 maybe, whatever that was. From here, it went from 30 to 48 or something, 38 or something like that. Here it went from 30 to 0, so that was actually a negative velocity, average velocity, and then those two happen to line up to be the same slope here, even though it wasn't going the same speed. The motion is a non-constant. When you have average velocity with non-constant motion, okay, then the average velocity is the slope of the straight line joining the initial and final points. Initial and final, initial and final. However you do that, the slope of the line joining the 2 points in question, that will be your average velocity. Okay? Always final minus initial. Okay? And since your displacement here is your vertical axis, this would be change of x over change of time. Change of x being negative over change of time, positive. change of action, very negative over change of time. Even though travel the thing, that still winds up with the same average velocity from AE as it is to AF. Average velocity between any point equals the slope of the blue line connecting those points. If you connect these 2 points, then it will be the slope of that line. These 2 points, whatever you choose to do, it's the slope between those 2 points. Okay, does that kind of make sense? Any questions? Okay. Now, if that is a measure of average velocity, what in the world would be a measure of instantaneous velocity? When I say instantaneous, what comes to mind? Average velocity, you went a certain distance over some time interval. What would be instantaneous velocity? The time interval has shrunk to near zero. Now, you can never divide by zero. So what you're dealing with is a ratio, and what the limit for the ratio is as that denominator gets close to zero. So the limit of the average velocity as the time interval becomes infinitesimally short, or as the time interval approaches zero, that's what your instantaneous velocity is. Okay? Now, I'm not caring for their notation much at all here. Okay, because that to me still looks like an italicized V. If you're talking about instantaneous velocity, you're talking about the vector quantity. Actually, those average velocities earlier, they should have been vector quantities, and they haven't indicated any of these are vectors. And that would be your limit as delta t approaches zero, delta x over delta t, where delta x is the change of your displacement. Okay. Now, let's go back to the slide. This is a 10-second time interval here. Started at A here, it went to B there. What happened in 5 seconds? Well, it started here and went to there. In 3 seconds to there. In 2 seconds to there, and 1 second there. And as you get closer and closer, this blue line is moving, the slope is moving closer and closer to what looks like the real slope of that red line, which ultimately, as your delta t goes to zero, will go from being a secant line here to a tangent line here. And a tangent line basically touches only at the point in question. In other words, the t final and t initial are the same, t0 or t10 or whatever it is, and that would indicate the slope of the tangent line right there. No longer a secant line that's doing like this, but a tangent line that only touches at the 1 point. Doesn't touch at 2, only touches at 1. And the line that grazes that curve right there, that would be your tangent line. So that limit, the instantaneous velocity, indicates what's happening at every moment of time. The magnitude of the instantaneous velocity is what you read on this card speedometer. Okay? That would be your instantaneous velocity, or at least a very good approximation of that. Okay? I'll leave that up for a while for you to get it. But if I were writing this, I would make sure that is indicated as a vector quantity, because it's a change of position, meaning a change of displacement over change of time. That should be a vector quantity here. And they're not indicating anything to let you know it's a vector quantity. Okay, everybody got it? Now, let me go back a slide again. The instantaneous velocity at point A would be the slope of that secant line as the time interval gets closer and closer to zero, which would be the slope of that tangent line. When they said at every instant it has a different, perhaps, instantaneous velocity. Right here it would be there, then there, then there, then there. Actually, right here, what appears to be the instantaneous velocity? What is the slope of the secant line, of the tangent line there? If it's a horizontal line, what's its change of y? 0. So that would indicate a 0. Because it's speeding up, stop, for an instant it stops as it turns and goes in the opposite direction. So that's a velocity of 0 right there. Instantaneous velocity of 0. Now here the instantaneous velocity here, 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 here. Every point in between, whatever the slope of that tangent line would be, that would be the instantaneous velocity. Okay? Now, again, notice here, the magnitude of the instantaneous velocity, indicating if it has a magnitude, you assume that's a vector quantity. The speedometer doesn't indicate what direction you're going, only the magnitude of that velocity. Okay. Which we call speed, because we call it a speedometer. But it's an instantaneous velocity. Okay, so the instantaneous velocity on a graph, the slope of the, this is what I was already saying, the slope of the line tangent to the position versus the time graph is defined as the instantaneous velocity at that particular moment of time. The instantaneous speed is defined as the magnitude of the instantaneous velocity. So to talk about instantaneous speed, that's what your speedometer is telling you, because at that moment, those directions are, well, speed doesn't have a direction, but that's the magnitude of that instantaneous velocity right there. And just because the denominator is approaching 0, the ratio may not be approaching infinity or 0 or anything else. It may be some other fixed value, which typically it is. Now, here's the graphical instantaneous velocities. Same thing I've been saying before, just represented on this graph. The average velocities are your blue lines. Between 1 second and 3 seconds, the average velocity was this. Whatever your change of, this is starting at, 5 meters, and going up to something like 51 meters. Over 3 seconds, that would be 51 divided by 3. Is that around 17? I believe it is. About 17 meters per second. Here at 2 seconds, it's looks like 5 to that would be 25 divided by something wrong. 25 divided by 2 would be 12 and a half. Actually, that's in what I must have done a little calculation wrong. Oh, goodness gracious. This is, I didn't subtract. 53 minus 5 would be 48. 48 divided by 2. 1 to 3. 48 divided by 2, 24. And the next one would be 25 divided by 1 would be 25 meters per second. Okay, that's making more sense. Then, in half a second here, it went 5 to 25, 20 meters per half a second. That's 40 meters per second. And then, what's this? 0.2 of a second, it went something a little bit greater than 10 meters. So you see, you can keep calculating that, and finally the green curve is the one. So this curve, see, this one and the green curve are not far off. This one and the green curve are almost the same. This tangent line is basically right on the money. Only intersects at that one place. Okay. You get an idea of the difference in average velocity and instantaneous. Instantaneous is the tangent line. Average velocity would be any of those, depending on where you took your final position to be. Make sense? Oh, wait. There was a quick quiz. Okay? This is on page 35. It's quick quiz 2.1. Now there's a figure here, and they don't show it in the slides, and that's sort of a pain in the neck. Okay? Figure 2.4 shows the unusual path of a confused football player. After receiving a kickoff at his own goal line, he runs downfield to within inches of a touchdown, then reverses direction and races back until he's tackled at an exact location where he first caught the ball. If you can picture that crazy scenario, okay? Probably tackled by his own team to keep him from hitting a safety. During the run, which took 25 seconds, what is the path length he travels? How far did he travel? He started at his own goal line, basically, went almost to the other goal line, and then turned around and came all the way back to exactly where he started. About how far did he travel? A 100 yards and another 100 yards. 200 yards in 25 seconds. Okay? So A was the path length he traveled, actually what he traveled, 200 yards. B, his displacement. If he started at his own goal line and then ran up there, turned around, ran back, and got tackled almost right where he caught the ball, what was his displacement? 0. Because he was tackled at the same place he caught it. His path length, 200 yards. His displacement, 0 yards. His average velocity in the x direction, x being down the field. Average velocity was 0, because it's displacement over time. What was his average speed? Distance traveled, 200, divided by time, 25 seconds. $200 yards divided by 25 seconds. 100 yards divided by 25 would be 4 yards per second. So he did 8 yards a second. Right? Let's check. I think they have those answers in the back somewhere. Let me see if I can find it easily. Probably not easily, but somewhere back here. Okay. Earlier I was looking for useful physical data quantities. I just found them. Appendix C, which is on A19. Your Earth-Moon distance, Earth-Sun distance, equatorial distance, mass of Moon-Sun, a lot of things like that. They're there. Okay. Standard symbols. Some fundamental constants, speed of light, those other things. That's on the next page, A10, also in Appendix C. So, those I was looking for before, there they are. Okay, we're in topic, not chapter, but topic 2. Quick questions, 200 yards, 0 displacement, 0 speed, 8 yards a second. Yes. Okay. I'm going to put a page back there so it's easier for me to find in the future. All right, I've got you in my roll book. I don't have to carry these home all the time. I'll put these here. Okay. There was quick quiz 2.1. All right. I think we've hit all those. On page 37, bottom of the page, is another example, slowly moving train. Again, if you're interested in seeing that worked out, please let me know. I'll be glad to work any of these examples out. But if I don't hear you request it, I'll assume you got it down. So please let me know. All right, we're ready for 2.1.3. There. Our new text is numbering these slightly different from the old one, so that's that. Acceleration. What was the velocity? Change of position per change of time. What's acceleration? Change of velocity per change of time. And guess what? If you're changing your velocity or your speed in your car, what instrument are you probably using? What pedal do you call that? Say again? If you're changing your speed? Okay.
Accelerator.
The accelerator, exactly. It's changing the acceleration. That's accelerating the car. Now, surprisingly, there's another pedal that's also changing your speed. What's that? The brake. That's slowing you down. That gives you a negative acceleration. There is one other device in the car that changes an acceleration. The steering wheel. Because remember, velocity is a vector quantity that includes magnitude and direction. Your steering wheel changes your direction, you just change the velocity. Okay? Because you're going in a different direction. So that's also an accelerator. So you really have three accelerators: the brake, the gas, and the steering wheel. So the acceleration is the rate of change of your velocity. Now here they put it in a bar, which means average acceleration, is, what does delta mean? Difference, meaning subtraction or change of velocity, final minus initial always over change of time, final minus initial. Your delta t is always what? Positive. Delta v may be positive or negative. If you started out fast, ended up slow, that's a negative velocity, change of velocity. You started off slow and ended up fast, then that would be a positive change of velocity, so acceleration. The units for velocity is SI unit. Unit for velocity, SI unit. Meter per second. Time is second. So that'd be meters per second, which is often called meters per second squared. That's the SI. CGS, centimeters per second squared. We use centimeters for your distance. Or US customary, feet per second squared. Though sometimes we use, now, if you talk about automobiles, someone's talking about what a hot car he has, what does he usually describe it as? It can do 0 to 60 in 4 seconds. Okay? What is he talking about there? What's 0 to 60? What's that? Yeah, it's change of speed. 0 miles per hour to 60 miles an hour in 4 seconds. That would be a change of distance, miles per hour per second. That's also an acceleration. Distance per time per time. It's just unusual units. US customary is feet per second squared. So anything that talks about a change of speed in a time over a time interval, that's an acceleration. Okay, so let's look at average acceleration. That's actually the formula we just saw. It's a vector quantity. Why is this a vector quantity? Because velocity is a vector quantity. These are velocities here, not speeds. And that's why I really didn't like to use the same symbol without any further indicator on it. Okay? So that's change of velocity over time. Time is a scalar quantity, so that would be a vector quantity. So therefore, acceleration is a vector quantity. Now, if you talk about its magnitude, yeah, that's fine. It's not a vector anymore. When the object's velocity and acceleration are in the same direction, okay, driving down the road, I'm increasing the speed, okay, that means I'm accelerating in this direction. That means when the object's velocity and acceleration are in the same direction, either positive or negative, then the speed of the object is increasing with time. So let's say I'm going backwards, so my speed is that way. And the speed starts off slow, but then increases going that way, so my acceleration is that way. Speed's that way, acceleration that way, that means the speed of the object is increasing with time. If I'm going this way, so velocity's that way, and it's increasing in that direction. In other words, acceleration is in that direction, then the speed is increasing with time. When the object's velocity and accelerations are in the opposite direction, so I'm going this way, but slowing down, meaning I'm accelerating that way, but still going this way, that means the speed is decreasing. Or, if I'm this, but going less fast, my change of velocity is that direction, but that means my acceleration is that way, my velocity is that way, so that means I'm slowing down. So when the object's velocity and acceleration are in opposite directions, the speed of the object is decreasing with time. Don't get speed and velocity crossed up. Speed is decreasing. Okay. Got it? Okay. Now, can you have a negative acceleration? Sure you can. If you're braking, that's a negative acceleration, right? A negative acceleration does not necessarily mean the object is slowing down. Okay, that means changing speed. It could be increasing speed, but this would be a negative acceleration. I'm going backwards slowly and then going backwards faster. That means a negative acceleration because I'm accelerating in that direction, but my speed is actually increasing. Speed, not velocity, but speed is increasing. If the acceleration and velocity are both negative, the object is speeding up, but in a negative direction. Deceleration means a decrease in speed, not a negative acceleration. So we use those two as if they mean the same, but they really don't. Deceleration means a decrease in speed, not a negative acceleration. Negative acceleration means I'm either backing up at an increasing speed, okay, in other words, changing velocity in that direction, or slowing down going this way, meaning my acceleration is that way, even though my velocity is that way. So that would be a deceleration, but not a negative acceleration. Going this way, but going faster, that would be not a deceleration, but it would be a negative acceleration. So, not that you really run into that many difficulties this way. I mean, this is just emphasizing the difference between precise physics speak and imprecise English. Okay, so don't get too tied up with this. Oh my goodness, y'all let 2:30 get by me, didn't you? You were supposed to stop me so we could do our lab. Okay, let's see if this is a good place to stop. All right. One thing, let's do a real quick quiz. These are true, false. A car must always have an acceleration in the same direction of its velocity. True or false?
False.
False, big time. B, it's possible for a slowing car to have a positive acceleration. True or false? Huh? Okay. If it's going in reverse but slowing down, that means it has an acceleration in the positive direction. So that is true. At least I think so. Okay? Number C, an object with a constant non-zero acceleration can never stop and remain at rest. An object with a constant non-zero acceleration can never stop and remain at rest. Beware of those nevers. Never say never. Okay? Here's where it could. Let's say a car is moving forward. Okay? And it's slowing down. So it has an acceleration in that direction. And it keeps slowing down until it stops and then starts. Constant, non-zero acceleration, but it did stop, come to a stop. So that would be, I think, false. So what do we have? False, true, false? Let's see what they had in the back. False, true, they said true. What's wrong with them? Let me see. An object with a constant non-zero acceleration can never stop and remain. And remain at rest. I'm sorry, I didn't say the last part. It can stop, but only temporarily. It will not remain at rest. Sorry. Okay. So from there, we're going to stop, and we will begin next time with instantaneous acceleration. Okay. That's right there. And that's page 39. Let me put my pages in place. And I didn't have much further to go, but I wanted to stop at 2:30, and you let it slip right past me. Okay? Shame on you. What I'm going to do is pause this. Nothing's projected right now, but you really don't need it now. Here's your lab sheets. This will be one of the shorter labs, and maybe one of the easier labs you'll do alternate. I guess this person's coming back. There was a person here, right? This person here, here, and here. You need 4. Okay. We need that one over. Okay. Is there anyone behind you? There was one back. There was someone back there, but that was good. All right, I think I've got them all passed out. Okay. People with triangles, just rest for a moment. People with just the meter sticks. 1, 2, 3. Okay. Get your meter stick. Okay. Now this one doesn't have what I need, but I'll demonstrate. This is the meter side. The back side of that is the inches side. Okay? So what you're asked to do, the 3 teams that have the meter sticks, okay, get your meter stick, flip it over, and write down how many inches that is using the inch sign. Now you'll see there's a fractional form there, so you estimate the fraction of an inch, convert that to a decimal. You see what I mean? That stick is 1 meter long, flip it over, and read how many inches that is. You see? And then estimate what fraction of an inch past the whatever that number is, and then convert that to a decimal. Does everybody understand that? The 3 teams that have the meter sticks. You got what I'm talking about? Don't go use a table somewhere. you're going to calculate your own conversion table. That's what you're going to do. Okay? Now, once you have how many inches that is, I'm just going to say this is not going to be a correct answer. Okay? Let me turn this on. Let me find a page that has a lot of white or a little bit of white on it. Let's just say, and this is going to be totally wrong, so don't use my thing here. I'll get my thing out from under here. Okay, you have the, where did that go? Okay, you'll find a lab with you, and somewhere near you is somebody who has either a meter stick or a triangle. Why don't you take the triangle that's right next to you there? No, no. Okay. No, you stay with him and use his meter stick, his triangle. And I'll have you take this triangle. And you'll be two, but you'll pick up somebody here, and you'll be two, and you pick up the other person. Okay? Now, but I'm only talking to the people with the meter sticks. So let's say you had 1 meter is equal to, this is going to be a wrong answer, so don't use it, 40 inches. Okay? Now, I want to take that and convert it to feet. Remember how you do your conversion? Blank blank equal blank feet. Okay? What you do first, okay? One of you two is with this team, and one of you two is with that team. I don't care which way you go. One of you is with these two, and one with those two over there. Are you three in the back together? Okay, I figured you were. Okay. How do you do your conversion here? You put your units in your place. What units go where? Between inches and feet. Put one on top, one on bottom. Which goes where? Which is? If you put inches on top, then you get inch squared per foot. That won't work, so you do it the other way, which is feet on top and inches on the bottom, because what you want to do, feet on top, inches on bottom, that way the inches cancel out, and that's, you leave feet where you want, okay, where you need it to be. How many feet in an inch or inch in a foot? Okay. Got 2 more people here. We got 16 scattered around the room. You each get in a different team. Okay? So don't give this team with 4. If you get with this one, why don't you get with this one, and we'll let me get a chair. So you back here, use this chair. Second. I know that you need to be with your team, and there's a team here and a team there, right? Is that how y'all split up? So one of you needs to be with this team and the other with that team. So one of you be with this team here, and you be with the team up here. So here's the chair. Okay. Now, I'll stand. What I was saying is, now you match the numbers with the units. How many feet in an inch or how many inch in a foot? 12 inches is 1 foot. So you multiply numerators divided by the denominators. So now you need a calculator. I hope each team has at least 1 calculator. Any of you teams don't have a calculator? Okay, good. So you do 40 divided by 12, that will give you the number of feet, right? And then you want to go feet to yard. You get a number here. Multiply this with blank blank equal blank yards. In this case, what unit goes in which place? Which unit goes here? Up and down. Feet or yards? Yards on top and feet on the bottom. And what's that conversion? How many feet in a yard? A yard in a feet? In a foot. 3 feet is 1 yard. So you take that number, whatever you wound up here, when you divide it by 40 by 12, you get feet. divide that by 3, you get yards. That's how you do your conversions, right? Now, the next one then says 1 inch equal so many meters times blank blank equal blank meters. Okay? Well, right here, you had 40 inches was 1 meter, right? So what you do here is divide this by 40 and divide that by 40. 40 divided by 40 will give you inches. 1 divided by 40 will give you meters. So you basically divide that by 40 to get inches, divide this by 40 to get how many meters are in an inch. It's going to be a very small number, by the way. You're dividing 1 by 40. So you see what, now don't use 40. I made up 40. It's an incorrect thing. You use the measurement that you got off your meter stick in a decimal form. You probably got it off as a fraction, convert it to a decimal, and then go. If you have any questions, please ask. Don't make some dumb errors. Okay? So ask me. Run things by me. Okay? Now, you folks with the triangle. Okay? You got 3 sides to the triangle, and all of you can listen up on this. Notice this is under 2. Short side. There's your short side, right? Everybody with a triangle. You see one triangle has a short side. There's a medium side. That would be this one. And there's a long side. Okay, now I'm going to start off giving this team the meter stick. I want you to measure that short side. Sorry, put you in the eye. Okay. Measure how many centimeters to the nearest tenth of a centimeter that short side is, the medium side is, and the long side. As soon as you get those 3 done, hand it to the next group that has a triangle. So get started on that right now and get to the nearest tenth of a centimeter. Here's a triangle. Where's the square triangle? Right back there. So wait, pass that around. Okay, those with meter sticks can start your calculations. Those with triangles, this team is going to take those, record them on the piece of paper, how many centimeters to the nearest tenth of a centimeter, and then middle side, long side, and test meter stick on the round. Okay? So those triangles have to wait just a minute until these get it. Okay? And then move on from there. Any questions? Meter stick should be moving now. Triangles, as soon as he finishes his, go faster to the next triangle team. I only could find one that worked. Now let's see. 2 people came in. I don't think I marked you present. Names? Second? Okay, Bria, I got you. Okay. Ann? Raven? Green, right? Okay. So we're just missing 1, 2, 3. Okay, that's it. Okay, we have now passed 4 o'clock, which means we're now in lab, technically. I mean, you've been doing lab. But Ife is here. Am I pronouncing it right? Okay. Nick is still here. Kiara's still here. Courtney Brooks is still here. Simone Cannon, we still haven't seen. James Graves, I saw him in another class, but not here. Raven came in. Shakina is still here. Charity didn't come in, did she? Okay. Courtney with a K is still here. I got you. Ambry is still here. Essence is still here. Ryan is still here. Valerius is still here. Darius, oh, I'm sorry. Monique is still here. Got it. Sasha is still here. Sasha or Sasha? Sasha's, I'm sorry. Sasha's still here. Allison's still here. Darius is still here. Scarlett's still here. Will is still here. Brianna's still here. Yeah, there you are. I knew you were, but I couldn't find you. Naya is still here. Bria came in. And Dakota's still here. Okay, if any of you have any questions, please ask. Don't guess. Make that first measurement on your thing. That's the wrong answer here. You find a better answer here. Put it in decimal form, inches. You'll read off the meter stick fraction, convert it to decimal, and then from that point on, fill out the rest of it. If you have any questions, please ask. Okay. Oh, don't do that. Measure how many centimeters that is. That's what you're at. Oh, you got it? Well, then pass it on to the next people. Okay. They've been waiting for you. Okay. Okay. All right, I'm going to pause the okay. So what number you just wrote down, then divide that by 12, and that gives you the number here. The number you wrote was how many of these are in the yard. That's not what you needed to write. This thing divided by 12, not 40. This thing divided by 12, that gives you that. That answer divided by 3, that gives you that. Okay. Now you can use the conversion tables in the back to check your answers, but don't get your answers from those. Calculate your own answers. Yes.
So this, you just want to like, you just want to different sides. You want me to sign
Okay.
actually didn't sign it.
I'm not sure. That's not what happened. Yeah, you just write down. I would say. Okay. Which you tell me. Okay. Okay. This divided by that. You calculate. Give me a second.
Oh, okay.
Yeah. And the same one. Okay. Yeah. You'll remember later. That's what down here would do.
So it's this.
Okay. Yeah. There it is. That's the way. What's that? For what? Okay. Okay. Are you calculating now or are you checking now? You got answer already?
Yeah.
Okay. You just look at them and see. Nice. Looking pretty good. I'm going from this one to that. Okay. 1 centimeter, that's right to the minute. Well, then you do the same thing you did up here. Divide by 3, divide by 12, just like right there. When you went from inches to feet, you divide by 12.
And then divide by 3.
And then, yeah, divide by 3. Okay. Don't guess. If you have questions, ask. Okay, yeah. That would be your medium size. Okay, you Was there another hand? I say, give me a hand. No, no. Okay. Yes, sir.
I got that from. Some of them I did really calculate. I just used it right. It's well, you just add a zero for this part.
I was
It's
thinking
for millions.
that's okay. See, you may actually have round-off error in addition to measurement error if you round it to 2%. By the way, that was an excellent point. I don't know if he meant to make an excellent point, but he did. You're making measurements, right? Anytime you make measurements, you have some type of error. Now, we found 2 meter sticks here that had different inch to meter conversions on them. About 1/8 of an inch different. That's fine. Use the one that you were given. No two, within one team, your answer should be the same. But the 2 teams could have not very different answers, but somewhat different answers. Okay? So you're taking a measurement. You will be introducing error just by your measurement. Then he also did a round off. And that could introduce a round off error that could complicate your measurement error. So, but it's fine. Just get close. Don't anticipate everything being exactly like in the back of the book. Did you find it the same as the back or close, Ife? Ife. When you looked at the answers in the back, did you find close or you haven't found them yet? Yeah, it was somewhere in Appendix A or C or somewhere back there, near the back. I don't know which ones they have either. I just saw, finally I found the conversions. Okay.
See, I've taken, I already took physics.
It was your job, though. I think my grades were down. I think I don't like that. W.
And this is stuff we didn't go through any of this stuff. We just started with where is it? Yeah, we started with like velocity and acceleration. But she took him when he had the online. And she never because the lab was online and everything was online. And he would send her the test. All the send it to like scan it. She was some other girl, she goes to UA.
I'll jump on the last day now.
I dropped out of that second and third test, like 1 and 30.
I jumped up to the third test. And then the last drop day was my drop. That is from
It was a bunch of foreign people, but we had he's a really nice guy.
I stayed in the office. Yeah, 8 o'clock here. Mom was 8 o'clock. I don't know, Friday the lab was 6 to 9 at night.
6 to 9 at night.
I'm okay with the lab. I can do 8 o'clock class.
This is not getting
The 8 a.m. this good.
Our lab is my mom shows up at a certain hour.
I made a 10 on the end
So
of the last
like the science, I can do.
from the homework. I'm sorry, I didn't
Yeah, homework. Did all the homework.
The homework brought me to yeah.
Did you see, we can ask review for it? My calculus teachers, leave the United States for less than a month. Full science.
All right. Another thing I'm going to pass out to you now, or just pass out, is your first test. This is on chapter 1, just so I won't forget to and no one will leave without it. Here's this, and yeah, that's one more.
When is due?
What's that? It's due a week from today. And these are how you can have it.
We had like 5 different sections.
I had about we take that few people every day. I was friends with
I didn't know you. So she knew. They said he was just.
Auburn's just unnecessarily hard.
I'm good. So catch me outside. Yeah. And he told me that
Our class average for second test was over 42.
yeah, I met him. That was before you were on the second test.
I made a 65 first test.
That's really good.
Yeah, it was.
It doesn't sound good, but it's good for him. Can I see the
Okay. Any other questions?